Good morning, everyone, or good afternoon, as it may be. I'm Jim Kasting. I'm a professor at Penn State University, and my topic for this workshop is Beyond Bare Detection to Biological and Geological Indicators. Before I get started, let me say that I'm old enough to remember Carl Sagan. This is the Sagan Summer Workshop. I knew Carl a little bit back when he was at Cornell University. In fact, I read his book, Intelligent Life in the Universe, back when I was an undergraduate, and that was one of the things that inspired me to go into space science. Frank Drake is also shown here. Frank Drake is well known for the Drake equation, also called the Sagan-Drake equation, and Frank pioneered the study, the search for intelligent life called SETI. Strangely enough, the search for intelligent life has proceeded before the search for life itself. And that's not because it makes sense logically, but because the technology for searching for intelligent life using radio telescopes has been around for a lot longer than the technology that we need to search for simple life. So let me give you a basic outline of the talk. I'm going to talk about three things. First, I'll start out with the basic requirements for life. Then I'll talk about the definitions and boundaries of the habitable zone, which are related to those requirements. And finally, in the last part, I'll talk a little bit about biosignatures and how we might look for them on exoplanets. All right, so let's begin with the requirements for life. I'll keep this pretty short and simple. I'll list three requirements here and then one on the next slide. I think one absolute requirement is that we need a planet with either a liquid or a solid surface. So a rocky planet, you could have a water world. Why do you need that? Well, you need a stable pressure temperature regime for life to evolve. If you have a gas giant planet like Jupiter or an ice giant like Neptune or Uranus, there's really no place convection goes very deep, and there's no place where a single-celled organism could get going. Second, you need a thermodynamic free energy gradient to drive metabolism and growth. All life needs some source of energy, otherwise it's not going to do anything. If you're at the surface of a planet, then there's plenty of free energy available from stellar radiation. And we're going, as I'll discuss in a moment, we're going to be mostly interested in surface life. So that's not really a big problem here. Third, you need availability of carbon and other bioessential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All life that we know it is carbon-based. Now, I used to read a lot of science fiction back when I was younger, and science fiction authors have thought about other possible forms of life, silicon-based life. Silicon's right below carbon in the periodic table, but I think it's really unlikely. Silicon, for instance, bonds with oxygen and forms things that we call rocks. So I'm going to assume that life is carbon-based. The fourth requirement is probably the most controversial of the ones that I've mentioned, and that's liquid water. So certainly for life on Earth, all organisms that we know of require liquid water during at least part of their life cycles. There are organisms, spore-forming plants, for instance, that can go for long periods without water, but they need liquid water to metabolize and to reproduce. There's a distinction in our own solar system. Earth is the only planet that has surface liquid water, but there may be subsurface liquid water on Mars and also on Jupiter's moon Europa and Saturn's moon Enceladus. Subsurface water is of great interest to NASA scientists who are sending spacecraft out to explore our own solar system, because we can eventually drill down beneath the surfaces of these planets and moons and look for evidence of life. But for astronomers who are observing exoplanets through telescopes, it's really not possible to do that. And so you need for life, for water to be present water and life to be present on the surface of the planet so that the organisms can modify the planet's atmosphere in a way that might be detected remotely. So that leads to a concept called eta sub Earth. And eta sub Earth is the fraction of stars that have at least one rocky planet in their habitable zone, the habitable zone being defined as the region where a planet, around a star, where a planet can maintain surface liquid water. So as I'll explain during the rest of this talk, the main utility of the habitable zone is to allow us to design space telescopes to look for such planets. And I'll also argue that we should be conservative in defining the habitable zone and in calculating eta sub Earth, because we don't want to undersize the eventual space telescope. All right, so this leads to part 2 of the talk, definition and boundaries of the habitable zone. I myself only learned just recently, this spring, that the term habitable zone goes back farther than I had thought. I'd been attributing it to Sushu Wang in a paper in 1955, but Ralph Lorenz discovered a couple years ago that the term actually was first used in a popular book by E.W. Maunder, Edward Maunder. And the book was called Are the Planets Inhabited? Came out in 1913. Maunder, for those of you who are familiar with sunspots, Maunder is famous among solar physicists for discovering what's now called the Maunder minimum, the apparent near absence of sunspots for about 70 years between 1645 and 1715. Now, my own interest in this subject was sparked back in the late 1970s when I was a graduate student at University of Michigan. There were 2 papers that came out by Michael Hart. Hart was a planetary science at NASA Goddard, and he defined the habitable zone in the way that I've mentioned, the region where a planet could maintain liquid water at some instant in time. Hart also defined what he called the continuously habitable zone, which is the region in which a planet can remain habitable for some specified period of time, which we usually take to be 4.6 billion years for our own solar system. Why the distinction? Well, all stars brighten as they age, as they convert hydrogen to helium in their cores. M stars brighten very slowly, but more massive stars like the sun brighten considerably. The sun was about 30% dimmer at the time that it entered the main sequence and has brightened since, and it'll brighten by another factor of 2 before it leaves the main sequence in another 4 or 5 billion years. Thus, if you can see my pointer here, if the habitable zone at some time t0 goes from here to here, then at some later time t1, it will have moved out and it goes from here to here. Then the overlap between those regions is the continuously habitable zone, which for that time difference between T0 and T1. There are people who don't like the name habitable zone, because to some people it implies that all planets within the zone should be habitable, which is not really the way it should be taken, but there's many different terms that have been used. The famous astronomer Harlow Shapley wrote a book in 1953 in which he talked about the habitable zone, but he called it the liquid water belt. Strughold called it the ecosphere in that same year. Lynn Margulis, who was briefly married to Carl Sagan, used to call it the Goldilocks zone, where the surface temperatures are just right. Francois Forget over in Paris has called it the hunting zone because it's the place where we might hunt for habitable planets. However, if you think about the search for extraterrestrial life, if we find a planet that might support intelligent life, then calling it the hunting zone is maybe not the right thing to do. And finally, there's a recent book out by Elizabeth Tasker where she calls it the temperate zone, because she argues that not all planets are in the habitable zone are habitable, but not all planets within the habitable zone are temperate either. So it's really just a choice of words, and I like Hart's terminology and Maunder's. Okay, but Hart's papers upset me when I was a graduate student because I was an optimist. I was a devotee of Carl Sagan, and Sagan, of course, thought that life was widespread within the universe and within the galaxy. Hart, on the other hand, concluded in the first of his papers in 1978 that the 4.6 billion year continuously habitable zone around our own sun is quite narrow, extending from about 0.95 AU to 1.01 AU. Inside of 0.95 AU in his model, you get a runaway greenhouse, which I'll talk about a little bit more in a minute. And outside of 1.01 AU, you get, in his model, you get runaway glaciation, from which you could never recover. He then, in the second paper, in the 1979 paper, he argued that continuously habitable zones around other spectral types of stars are even narrower. And so pessimists picked up on that and concluded that Earth might be the only habitable planet in the entire galaxy. So that got me interested as a graduate student, because I wanted to learn enough to see whether I could poke any holes in that argument. Okay, there are problems with Hart's model that many people have recognized. Hart concluded, incorrectly I'll argue, that a fully glaciated planet could never deglaciate by building up CO2. He actually had a feedback in his model that allowed CO2 to build up on a frozen planet, but he underestimated the greenhouse effect of CO2. If you look at the Earth's long-term climate record, which is something that my students and I do much of the time, you find out that there's strong evidence that the Earth actually did freeze over 2 or 3 times in what are called snowball Earth glaciations. And of course, the Earth did recover, and there are capped carbonates on the top of the glacial deposits that indicate very strongly that it recovered by building up CO2 in its atmosphere. So let me talk about the CO2 buildup. There's a well-known negative feedback that causes CO2 to accumulate on frozen planets. Here's a diagram that shows what we call the carbonate-silicate cycle. It's part of the carbon cycle. So the carbon cycles in different ways. The part of the cycle that most people are familiar with is what we call the organic carbon cycle. You have photosynthesis going in one direction, converting CO2 and water into organic matter and oxygen, and that's balanced by respiration and decay, which goes the other way. That's the fast part of the carbon cycle. But on long time scales, the more important part is sometimes called the inorganic carbon cycle, but it's also called the carbonate-silicate cycle, and it's illustrated in this cartoon here. If we start on the left, CO2 from the atmosphere dissolves in rainwater. That gives you a weak acid, carbonic acid, which is weak enough that you can drink it. It's the acid in soda pop, but it's strong enough on long time scales to dissolve silicate rocks on the continents, represented here by the simplest calcium silicate mineral, CaSiO3. Calcium silicate plus 2 CO2s plus water gives you calcium ions plus 2 bicarbonates plus dissolved silica. And these byproducts of weathering then collect in groundwater and in streams and rivers and flow down to the ocean. And there, organisms that live in the surface ocean mostly use the calcium and bicarbonate to make shells of calcium carbonate. And 1 CO2 is actually released in that process. Now, when the organisms die, they fall from the surface ocean into the deep ocean. Most of the calcium carbonate redissolves because the deep ocean is more acidic than the surface ocean, but some of the carbonate survives. It's deposited on the seafloor, forming calcium carbonate sediments. The seafloor, as we know from the geophysicist is not just sitting there, it's being created at mid-ocean ridges, and it's being subducted at various plate boundaries through the workings of plate tectonics. So when the subducted plate goes down, some of the calcium carbonate sediments are scraped off, but some of them are carried down to great depths where calcium carbonate recombines with silica, which by this time is the mineral quartz, and undergoes a process that we call carbonate metamorphism that reforms calcium and magnesium silicates and releases gaseous CO2, which then comes back into the atmosphere through volcanism. Now, this process is slow. It's slow enough that you can think of the atmosphere and ocean as one combined reservoir. This process recycles all of the CO2 in the combined atmosphere-ocean reservoir on a time scale of about 500,000 years. It's also temperature dependent because the weathering reactions shown here on the left require liquid water. The gas phase, reactions between gas phase CO2 and solid minerals like calcium silicate don't go appreciably at any temperature. So when the climate gets too cold, then silicate weathering slows down, or in the case of snowball Earth, it may stop entirely. But volcanism continues, and so CO2 builds up in the atmosphere until you get enough greenhouse effect to melt the ice. Now, there is a caveat to this, which I'm not going to have time to discuss, but if you have a planet that has low volcanic outgassing or low stellar insolation, then you may not get a steady state warm solution from this, but instead you may get a process that we call limit cycling, where the climate varies back and forth between snowball conditions, globally glaciated, and warm conditions. And so some planets near the outer edge of the habitable zone that have weak volcanism may be technically habitable, but only part of the time. Okay, so with that thought in mind, this is the basic problem with Hart's model, was that his outer edge of the habitable zone was, we think, too close in. And so when you allow for CO2 buildup on the outer edge through this carbonate silicate cycle feedback, then the habitable zone in our models turns out to be relatively wide. Here's a diagram of, we did a paper on this way back in 1993, and this is a diagram that was actually made by some European scientists, much prettier than the diagram that we had at the time. So this is labeled the ZAMS habitable zone. ZAMS, of course, is zero age main sequence. Remember that the habitable zone is a time-dependent concept, so that all stars brighten as they age, and therefore their instantaneous habitable zone has to be defined at some time for them. Sorry, let me go back to that. So here, the axes are distance in astronomical units on the x-axis, and the mass of the star relative to the sun on the y-axis. You can see here at the time, 9 planets in the solar system. Pluto's drawn with an X through it because since this slide was made, Pluto has been deplanetized. But you can see that here's the 4 innermost planets, Mercury, Venus, Earth, and Mars. At zero age main sequence for the sun, 4.6 billion years ago, Earth was sitting smack dab in the middle of the habitable zone, which is shown by this blue region. And Mars was just outside of it. So just by eyeballing this, you can see that the width of the habitable zone in our models is comparable to, or even a little greater than, the mean interplanetary spacing in the inner solar system. So the chances, if you have other planetary systems that have spacings of planets like our own, then the chances of finding one in the habitable zone would be pretty good. But of course, you all are studying precision radial velocity measurements, and we know that many planetary systems are not like our own. So this is really an unknown that we have to discover. There are limits to how well this feedback can work. If you get too far out, then the CO2 starts to condense and form, usually it forms a solid rather than a liquid. But this has two effects. Besides removing CO2, if it condenses all the way to the surface, you can form CO2 clouds in the upper troposphere, and that reduces the greenhouse effect by lowering the tropospheric lapse rate, the rate at which temperature falls off with altitude. An equally important effect is that CO2 is a very good Rayleigh scatter. It's about 2.5 times as effective as air. And so when you build up a dense CO2 atmosphere, that raises the planetary albedo, and that works against the greenhouse effect of CO2. So that leads to a concept that we call the maximum greenhouse limit, which is the maximum amount, a distance at which you, from a star, at which you can warm the planet with CO2. And that occurs in our models at about 1.67 astronomical units for a star like the Sun. Mars, by comparison, is at 1.52 astronomical units. So Mars is within the habitable zone today. Near the inner edge of the habitable zone, the problem is just the opposite. The planet can develop either a runaway greenhouse or a moist greenhouse. The runaway greenhouse, at least the way I define it, is that's the point at which the oceans evaporate entirely. In our old model from our 1993 paper, that runaway limit was at 0.85 astronomical units. There's another limit that in the old model happened considerably earlier, at lower solar luminosity than the runaway. We call this the moist greenhouse. And in this situation, the ocean remains liquid, but the stratosphere becomes wet, leading to rapid photolysis of water and escape of hydrogen to space. So this was actually something that was shown way back in 1969 by Andy Ingersoll. And that is what really limits the inner edge of the habitable zone for, because planets lose their water inside of that. The old limit was 0.95 astronomical units, and as I'll show in a moment, that's where we think it is again today. Now, several years ago now, in 2013, my colleague Colin Goldblatt wrote a paper where he showed that if you use newer absorption coefficients for water from what's called the HITEMP database, then the whole runaway greenhouse story changes considerably. Most of our old models, our really old models, use band models. Most modern climate models use what's called the HITRAN database. Colin used the HITEMP database, and HITEMP is a newer database that's based strictly on quantum mechanical calculations. The HITRAN database includes hundreds of thousands of absorption lines of species like water and CO2. The HITEMP database includes billions of lines. Computers are fast these days, and so you can do that. And these are weak lines, which don't make much difference for climates like the Earth, but when you get into a warm climate with lots of water, then the HITEMP database predicts that you can get water absorbs throughout the visible all the way down into the near UV. So to make a long story short, on the right you see the old 1988 model, which runaway greenhouse, on which our 1993 paper was based. Surface temperature on the x-axis and planetary albedo on the y-axis. You can see that as you get to hot temperatures into the runaway regime, the asymptotic albedo was about 0.35 or so, whereas in Colin Goldblatt's model, if you look at just this pink curve down on the bottom, that's for the HITEMP database, the albedo is about 0.17 in that same regime, about half what it was in the old model. So that means that with those new coefficients, the planet is much more susceptible to runaway conditions. So some students of mine, my postdoc Ravi Kopparapu and then graduate student Ramses Ramirez, went back and revisited the habitable zone calculations using the HITEMP coefficients derived from the HITEMP database. And we found that the habitable zone moved outward here. Now, this is a figure from our 2013 paper. Ravi Kopparapu was the first author. The habitable zone, instead of showing it in terms of distance, we're showing it in terms of effective flux. And then on the vertical axis, instead of using stellar mass, we're using stellar effective temperature. So what this does is this expands the habitable zone and allows you to see the differences between different stellar types. If we just look up here at about 57, 80 Kelvin, that's where the sun's effective temperature. This blue dot here is the Earth, and the green dot is the conservative habitable zone. You can see the Earth is lying right on the moist greenhouse limit, and this black curve to the left of it is the runaway greenhouse limit. In other words, with the new coefficients, our model predicted that the present Earth is on the verge of losing its water. Well, we knew that's not correct. The model assumes a fully saturated troposphere because it's really difficult to treat relative humidity in the water cycle properly in a 1D model. So we knew that that result is not really correct, but that's what you get in 1D. If you really want to do climate models well, you need to go to three dimensions. And fortunately, that same year, in 2013, a paper came out by Jeremy LeConte et al. LeConte was a postdoc then at with Francois Forget's group over at University of Paris, and they used a 3D model to study the runaway greenhouse problem. And this is just one figure from their paper. Sorry. So with a 3D model, you can do the general circulation of the atmosphere. One common feature of the Earth's atmosphere and these moist atmospheres, hot, warm, moist atmospheres that they study is that in the tropics, you get Hadley cells where you have rising air at the equator and descending air at 20 to 30 degrees latitude. In the regions where the air descends, the water vapor has already rained out. It rained out in the ascending branch of that Hadley cell. And so the descending branch is strongly undersaturated, and therefore that's shown by these white dots here. We're looking at relative humidity contours. So the outgoing infrared radiation that cools the Earth can get out through those windows in the Hadley cells. In fact, the technical term, well, the popular term for these is radiator fins. And this was actually not a phenomenon that was discovered by LeConte et al. It was pointed out in a paper 20 years ago, 25 years ago now, by Ray Pierre Humbert in a paper dealing with Earth's tropics. So we now adjust our habitable zone boundaries, taking into account those results from LeConte et al. There are researchers who don't trust theorists or climate models, and so I mean, there are still problems with the climate models. If you are skeptical of those, we can also derive empirical limits from our own solar system. The top picture here is a radar, synthetic aperture radar imager of Venus from the Magellan spacecraft, which can see through the clouds. And if you see the surface of Venus here, we don't see any evidence of flowing water. We think that Venus was resurfaced between 500 million and 1 billion years ago, and it hasn't had water on its surface since that time. So that gives us an empirical limit on the inner edge of the habitable zone, which we call the early Venus limit. Mars, by contrast, if you look at the bottom feature, this is one of the valley networks. It's Warrego Vallis. There's lots of evidence from Viking and from more recent spacecraft that there was liquid water flowing on Mars' surface at and prior to 3.8 billion years ago. So Mars looks like it was habitable, even though it's slightly outside our estimate for the outer edge of the habitable zone. If you combine all that, then here's an updated habitable zone as of about 2013 or 2014 from the Kopparapu et al. Paper. Again, the habitable zone is shown in terms of effective stellar flux and effective stellar temperature on the vertical axis. Here is Venus, Earth, and Mars in our own solar system. The runaway greenhouse is in yellow. The recent Venus limit is in red. The maximum greenhouse limit is blue, and the early Mars limit is orange. These objects down below are various exoplanets that we knew about at that time, mostly from the Kepler survey. Now, so we like to use the term conservative habitable zone for this region that we calculate with climate models, the runaway greenhouse and maximum greenhouse limits. Notice that Earth is now safely away from the runaway greenhouse, and that's because we've adjusted these limits to account for the 3D calculations by LeConte et al. If you're more optimistic, then these planets over here within this reddish region might be habitable because they're within the recent Venus limit, and so that almost doubles the width of the habitable zone in this space. But you know that's not in agreement with at least those climate models. Now, finally, 7 years later, we've adjusted the habitable zone. The habitable zone is still the same here, but the planets have changed. I should say that these new figures are all done by my former graduate student, Sonny Harmon, who's now out at NASA Ames. He's a very good graphics artist. What Sonny has done in this version of the habitable zone is to eliminate all exoplanets that have masses greater than that have radii greater than 1.6 Earth radii, because as you probably have heard during this workshop, we think that about 1.6 Earth radii is the upper limit for a rocky planet. Let me just point out two sets of planets here that are very important. At the very bottom here is the TRAPPIST, 4 planets from the TRAPPIST-1 system. 3 of those, E, F, and G, are in the conservative habitable zone. TRAPPIST-1D is in the optimistic habitable zone. At least these 3 outer objects are likely targets for JWST. These, of course, were discovered by transit spectroscopy, by transits, and so we can do transit spectroscopy on them with JWST. The other planet that's of great interest is this one right here, Proxima Centauri B. This is a non-transiting rocky planet in the habitable zone of Proxima Centauri, which was discovered by RV measurements because it doesn't transit. And that one is a good target for observations by these upcoming really large telescopes like the ELT, 30-meter class telescopes, which I'm not going to talk more about in this talk, but which is certainly interesting to the ground-based astronomers. Okay, so this brings me to the last part of the talk on atmospheric biosignatures and how to look for them. I'll be brief here. There's lots that could be said, but we don't have infinite amounts of time. The technique that looks most promising to those of us who are astrobiologists is called direct imaging. Almost all the spectra that we have of planets right now are transit spectra from Hubble and Spitzer. James Webb will do a better job on transit spectroscopy, but you're still only looking at transiting planets, and that excludes planets around most of the nearby stars. And of course, it works better for M stars than for G or K stars because the odds of a transit go up if the habitable zone is closer in. In direct imaging, you're trying to block out the light from the star and look for either reflected light or emitted infrared radiation from the planets around it. So direct imaging is what we really hope to do in the future. NASA's been studying the direct imaging telescopes for a long time. Back in the late 1990s, Chaz Beichman, who is one of the organizers of your workshop and hopefully is watching this video, ran a working group, which Chaz was the leader of and I was a part of for several years. This is one of Chaz's slides here that he used to show to illustrate the problem. Wavelength in microns on the x-axis. So in microns, the visible goes from 0.4 microns to 0.7, so down in this region right here. This is a measure of flux on the vertical axis, and this is the sun and the Earth seen from a distance of 10 parsecs. The sun is up here at the top. It's nearly a black body, and it's very bright compared to the Earth. The Earth's emitted and reflected flux is shown by the curve down here, the black curve at the bottom. You can see that it parallels the sun's curve here in the visible and near IR, and that's because you're seeing the Earth there in reflected light, and then this second hump in the Earth curve, that's the thermal infrared, where one is looking at emitted infrared radiation from the Earth. Both of those have absorption features in them, which I'll talk about in a minute. Now, back in the late 1990s, the real question was which wavelength is better for doing observations. The contrast ratio between the planet and the star is much better in the infrared than it is in the visible. In the visible, the sun is about 10 to the 10th times brighter than the Earth. In the infrared, thermal infrared, the sun is only 10 to the 7th times brighter. And so NASA and Chaz at the time were thinking that, we were initially studying a mission in the infrared. So TPF stands for Terrestrial Planet Finder. The I stands for interferometer. As I'll show you in a moment, you need an interferometer to do this mission in the visible. So the contrast ratio is better in the thermal IR, but you run into the diffraction limit. Theta is approximately lambda over d, where lambda is your observation wavelength, d is the diameter of your telescope. Real telescopes operate at some multiple of lambda over d. And if you go through the math on this, in the visible, you need about an 8-meter telescope diameter, and in the infrared, you need about 80 meters. Well, we're not close to sending up an 80-meter filled aperture telescope to do the infrared. So NASA's original idea was to do an interferometer. It was called TPF-I, and here's one design for it. It had 4, I think they were 2.5 or 3-meter telescopes mounted on an 80-meter boom, so that you could do interferometry with them. There would be a beam combiner back here in the center. Now, the disadvantage of this concept is that you have a fixed baseline, which you can't adjust, and you also get vibrations. In fact, NASA studied another mission called SIM, the Space Interferometry Mission, which would also have used interferometry to try to do very accurate astrometry. But they found out there was a SIM test bed at JPL, and they found out that booms vibrate on a variety of scales. And so that was always a problem for the original TPF-I design. Now, ESA picked up on this, the European Space Agency, and they studied an infrared interferometer called Darwin. So instead of having the telescopes mounted on a boom, they had 4 free-flying telescopes here, and then a 5th spacecraft back here, which was where the beams were combined. So that ESA studied this mission for at least 15 years. Alain Leger was the PI on this, and finally it got dropped by ESA. I should have said TPF got dropped by NASA too. But the good news is that ESA is now studying the infrared interferometry again with a mission called LIFE, the Large Interferometer for Exoplanets. And I personally am really happy to see that happening. If we do eventually get an infrared mission, then you can get really good biosignatures and other atmospheric signatures of gases. Here's an old figure from TPF-I days showing moderate resolution spectrum of Venus at the top, Earth in the middle, and Mars at the bottom. This is in the thermal infrared from about 8 microns out to 25 or 30 microns. For Venus and Mars, their atmospheres are CO2 dominated, and all you really see is the very strong 15 micron band of CO2. For Earth, even though it has much less CO2, you still see a strong 15 micron band, but you also see strong water bands. This is the rotation, pure rotation band of water vapor out here, and these are vibration rotation bands. And here at 9.6 microns, there's a strong ozone band. That ozone, of course, is produced from molecular oxygen, and oxygen, most of it in Earth's atmosphere, is produced from photosynthesis. So that's a potentially good bioindicator. Now, back to the history of this again. NASA decided to switch. They got better at doing coronagraphs, and the coronography techniques improved, and so NASA worked for a mission for a while on a mission called TPF-C, Terrestrial Planet Finder Coronagraph, and I was part of that group that worked on that back in 2005, 2006. So here, whoops, sorry, this is a picture of TPF-C. That's the big sunshade around it. The mirror, it was an 8 by 3.5 meter elliptical mirror, which would have looked for reflected light from planets around stars. NASA has been studying missions like that since then. TPF-C got dropped, but in the past 3 or 4 years, NASA's been studying 2 big direct imaging missions, one called LUVOIR, the Large UV Optical Infrared Space Telescope, and one called HABEX, the Habitable Planets Explorer. LUVOIR, which you've probably heard of, has 2 different versions. One is 8 meter and one is 15 meters. They're both quite large. HABEX is smaller, only 4 meters, but at least some versions of HABEX also fly an external star shade, which you can use to, if you find a really good candidate, you can use that to get good nulling on the star and also get a good spectra. So if you do get spectra of a planet like modern Earth, you might see something like this. This is a figure from way back in 2002 from Nick Wolf and colleagues out at University of Arizona. For years, the TPF working group had wanted to get a single pixel resolution spectrum of the Earth. And it's hard to get from an Earth orbiting spacecraft because you're too close. And so we talked about sending a spacecraft out to Earth-Sun. We talked about sending a spacecraft out to Earth-Sun L1 to get a single pixel image. Well, these guys were smarter than that, and they went up on Kitt Peak and turned their telescope on the moon, shown up here in the upper left. When the moon's in crescent phase, of course, there's the bright part of the moon where you're seeing reflected sunlight, but on a dark night, you can also see the dark part of the moon. And why is that? Well, that's being illuminated by light from the sun that bounced off the Earth and then bounced off the moon and back to the Earth. So within that spectrum is an Earth's atmosphere spectrum. If you subtract the spectrum of the bright side from the spectrum of the night side, you get the Earth spectrum. That's shown up here in the top by the black line with a relatively high resolution spectrometer. The scale is in angstroms now, so that the visible goes from 4,000 to 7,000 angstroms up here. And then down here on the bottom, this red curve is a model fit to the data. So it's easier to look at the red curve here. In the visible, there's a broad absorption band by ozone. You can see 3 vibration rotation bands for water, here, here, and here. And then most interesting of all, there's a couple of absorption bands of O2, especially this one at 7,600 angstroms or 760 nanometers. That's the O2A band. And it's a forbidden transition, but because there's so much O2 in the Earth's atmosphere, it's actually pretty strong. And so all of these telescopes would have spectrometers which are designed to be able to resolve that O2A band. So let me leave you with a few conclusions then. First, detectable life requires at a minimum a planet with a solid or liquid surface, a source of thermodynamic free energy, sufficient availability of carbon, and surface liquid water. Second, habitable zones should be defined conservatively if they're being used to generate design parameters for future space-based telescopes. And as I've emphasized in this talk, 3D climate models are really the state of the art. So if you want to do better than we've done on the boundaries of the habitable zone, you probably need to go to 3D. And then the really exciting thing is that in the long run, both NASA and ESA would like to do these big space-based direct imaging missions to get spectra of planets in both the visible and the thermal IR. And so that's our best chance of finding Earth-like planets and for looking for signs of life. Okay, thank you. And I look forward to seeing you all remotely when I give this talk in a month or so.